Hey, welcome back. Let's finish up our discussion on acids and bases by talking about a quick topic, which are called titration curves. So we already know what a titration is. A titration is when we add an unknown acid or base to a known acid or base in order to either determine concentration or molar mass. But we can look at titrations and predict values about titrations through something what's called a titration curve. Now understand a titration curve is set up doing the pH versus the volume of the titrant used. So titrant is a little bit of a vocab term. The titrant just means the thing that's in the burette. So that is what the titrant is. It's the thing doing the titrating. So let's look at a graph. Let's do a strong acid with a strong base. Let's say that we have a 0.1 molar HCl, and we're going to titrate that 0.1 molar HCl with 0.1 molar NaOH. And let's get an understanding about what we're looking at here. So the strong acid is the thing that's in the flask, and the strong base is the thing that's in the burette. So this is actually very similar to, say, like what we did in our lab, where we had the flask was our HCl and our burette was our NaOH. So if we wanted to set up a graph for this, we would put our axes down like so, and on the y-axis we're going to put pH. And on the x-axis, we're going to put volume of whatever's in the burette. So this would be volume of base. All right, so let's think. We want to first start by writing what our pH is in our flask before we start titrating at all. So this is an acid in the flask, and we want to figure out the pH. So if you want, take a second and see if you can calculate the pH before we titrate at all. So that means that we would want to take the 0.1 molar HCl, find the concentration of H+, take the negative log, and that would be our pH. Just give it a second. It'd be a little good practice. Come on back when you're... You may have realized as you were maybe fumbling around that you think, oh, it's actually a lot easier than I think Womack's thinking it is. It should just be 1, right? Like the pH, the negative log of 0.1 is just 1. So I wasn't asking you to do anything too tough. So that's the concentration that we're going to start at for our titration curve. So then here's what happens. When we add an amount of base, we would notice that the pH doesn't really change that much as we're adding base. But then there comes a point where even adding a little bit of base shoots the volume up. Let's see if I can do that a little better now. So we're going to go like this, and then like this. So this is not a lot of volume. It changes the pH very drastically. So it's kind of like this idea that in the flask, at one point, there's more acid than there is base, and then just all of a sudden, boom, there's more base than there is acid. And as soon as there's more base than there is acid, the pH shoots up. And this point, kind of somewhere in the middle here, this would be the equivalence point. And remember, the equivalence point is when the moles of acid equal moles of base. And if we are looking at the pH of the equivalence point, for a strong titration, the pH is going to be 7 at the equivalence point because the concentration of H+ equals the concentration of OH-. And that's about it. It's really not that much more complicated than that. Let's look at another one. So we have this one here that's weak strong, but I want to come back to that later. Skip down a little bit. Let's do strong base, strong acid, just so we can keep consistent. Because now this is what's in our flask, and this is what's in our burette. So it's kind of the same titration, except we're going a little backwards. This time we have 0.1 molar NaOH. And we are going to titrate it with 0.1 molar HCl. So, I don't know why I put a dot there. Let's put our axes back down. And this time, if you were to take the negative log of 0.1 molar, you would find that you get, 1 again, but that would be POH. So then I would do 14 minus 1, that would give me 13. So my starting pH this time is going to be 13, and I'm going to have down here, I'm going to have volume of the acid. So this is the thing that's in the burette. So this is going to be very similar, where we're going to be adding an amount of acid, and it's not going to do anything at first, and then all of a sudden, boom, and then it drops down. Okay, and your curve could probably look a little better than that. Let's see if I can make mine a little better. There we go, like this, more of a curve. And very similarly to last time, this point here in the middle, this is the equivalence. And if I were to determine the pH at the equivalence point, I would most likely find that it's 7. My graph isn't exactly to scale, but that's the point, right? So again, we have a lot of base in the flask, our pH is high, there comes a point where eventually our equivalence, we reach equivalence and then we drop straight down and our pH starts to decrease. So that's what it looks like if it's a strong, strong. It's a little more interesting if it's a strong, weak, or a weak, strong. So let's look at this one. This time we have a weak acid in the flask, and we have a strong base in the burette. And this time we're going to do 0.1 molar acetic acid, and let's titrate that with, oh, let's just, I don't know why I put the dot again. Let's say consistent, let's do NaOH. And this time, we're going to have a acetic acid with a Ka of about 1.8 times 10 to the -5th. So let's set up our graph again, just like this, just like that. This is the volume of our base, and this is the pH. Now I'm going to put 1 here on the graph, but I want you now to take a second and see if you can determine the pH starting before we do anything. So what is the pH of the acetic acid before we begin? You might need an ice table for this. So take a second, see if you can calculate the pH before we start, and then come on back when you're done. So hopefully you got like about 2.8-ish or so. I'm going to put 3 on the graph, and I'm going to put my dot down here. The important thing to take away here, after you have calculated, you should have noticed that our pH is higher in this solution than it is with the strong acid because we are dealing with a weak acid here. So the graph is going to be shaped somewhat similarly in that we are going to have a steady increase and then a very large increase and then a steady increase again. Now, here's what's different. This is the equivalence point, which is true. I'm going to abbreviate it as equiv point like this. That's the equivalence point. But if we were to draw this equivalence point over to the pH line, we would notice that this pH is actually somewhat above 7. That's interesting. Let's look at the equation that this forms. So let's write out the equation. This should be CH3COOH plus NaOH. And this is going to do a little bit of double replace. So we're going to have H2O and NaCH3COO. Now, this substance here, this is what's in solution at equivalence. This is what's called a basic salt. The reason why we call it a basic salt is because it is a salt that in solution, it has a pH above 7. But this NaCH3OO- causes the pH to be above 7 when we're at equivalence. Now, there's actually something else that's really interesting here. This section right here of our titration where we're not really increasing the concentration, or excuse me, the pH at all, this is actually a buffer. And it's sometimes referred to as a buffer region. If you're looking at that equation that we just wrote right there, can you see that there is a buffer present in solution? Well, you might be able to recognize it. Remember that a buffer is the acid with its conjugate base. So if we were to rewrite this, you might notice that it's CH3COOH plus OH minus, because we don't really care about the NaOH, and that gives us H2O and CH3COO minus. These two things form our buffer. We have the acid and its conjugate base. So that's one of the key differences between weak strong and strong strong, right? So again, for a weak acid and a strong base, equivalence is going to be higher than 7. It is not going to be at 7. So let's look at another one. You might be able to guess what the pattern here is. Let's do now a weak base with a strong acid. So this is what's in our flask. And this is what's in our burette. This time, let's do ammonia. So 0.1 molar NH3. And we're going to titrate that with 0.1 molar HCl. So, just like last time, see if you can find out the pH of this solution before we even start titrating. So this time you'll probably find the concentration of OH minus, and then you'll use that to find pH. So go ahead, give it a try, and come on back when you're done. Hopefully you found that the pH is about 11.1, right? You run through it, you got 1.8 times 10 to the negative fifth, multiply that by 0.1, take the square root, you do 14 plus the log of that number, that gives you the pH. So the point is that it's below 13. So let's draw our curve. This time we're going to have a steady decline, not that much, hold on, steady decline, and then big drop, and then down like this. So in this situation, let's say that our equivalence point is somewhere around, like here. This is the equivalence point. And we would notice that the equivalence point is at some point below 7. So why do you think that might be? Well, let's look at the equation again. So if we have NH3 plus HCl, this is just going to form a acidic salt, NH4Cl. And again, this acidic salt is going to bring the pH below 7. So if I have a weak base titrating with a strong acid, my equivalence point has a pH below 7. That's really the big takeaway that I want you to have here. A pH below 7. So we also have a buffer region, just like last time. This region here, this is a buffer region. And we should be able to recognize that the buffer exists because we have the weak base, and inside of the salt we have the NH4+, which is its conjugate acid. Both of those things are present in solution, which is what's causing that buffer to occur at the beginning of this titration. After we get past that point, there's no more buffers. But the reason why that point does not change in pH so quickly is because there's a buffer present. So that's it. Those are titration curves. And again, this isn't something where you're going to have to do any sort of math or anything with these titration curves. If anything, you might have to interpret them or maybe jot down a couple on your own. But it's just kind of important to take away that strong titrations always just have a pH at equivalence of pH of 7 at equivalence. So strong acids go up, strong bases go down. And then when you have weak acids and strong bases, or weak bases and strong acids, the pH is going to be above 7 or below 7 respectively, and there's a buffer occurring at the beginning. It's really the big takeaway. So just make sure that you understand what these graphs are telling you, and see if you can interpret them in the future. We'll see you next time.